Okay. Good evening, children. Atomic structure lesson. Today we are going to learn some topics about the discovery of nucleus, that is alpha particles, and then what are the postulates of Rutherford's atomic model and Bohr atomic models. Okay. First, we are going to learn the concept of discovery of nucleus. Lord Rutherford. This is the scientist name is Lord Rutherford. From New Zealand. So he did one experiment regarding that atom, the bombarding of, he took that gold foil. Okay. So the bombarding of thin gold foil with a very small positive charge particle is called as alpha particles. Yes, he took that gold foil for his experiment. He bombarded that alpha particles through that gold foil. So he selected gold foil because it is very thin layer. So the experiment is possible to do that. Okay. So that the Lord Rutherford, scientist from New Zealand, he did a famous experiment of bombarding of the alpha particle using gold foil. So gold foil is the equipment for the experiment. Okay. So what some details? So what are the details of that experiment means? Most of the alpha particles are passed through that straight line. So the first point is most of the alpha particles. He send the alpha particles to the gold foil. So most of the alpha particles pass straight line only. So this is the first observation of his experiment. Okay. Straight lines are straight through the foil. And next point is some alpha particles are slightly deflected. Some particles are slightly deflected in that area. So the straight line is deflected. So the third point of his experiment, he concluded very few alpha particles are completely bounced back. Okay. Very few particles are completely come back. Bounce back. So these are all the conclusion of his experiment. So Rutherford, the scientist from New Zealand, did one experiment. With the help of the gold foil, the alpha particles are sent through the gold foil. He observed the details. Most of the alpha particles pass in the straight line, straight through the foil. And then some of the alpha particles are slightly deflected, and then very few particles are completely bounced back. So these are all the conclusion of his experiment. So did you understand, Pa? Is that clear? Yes. This is the atom. So he sent the alpha particle. The center part is called as a nucleus. The center particles of an atom is called as nucleus. So he sent the alpha particles. Most of the alpha particles are go through that straight line, that is through that foil. So these are all that straight line alpha particles. Some alpha particles are slightly deflected. So this is the first point. So these three are passed in same, that is straight line. This is the second point. that some lines are deflected in that area. So the third one is some alpha particles are bounced back. Yes, come to that same way. So this is the third point of this experiment. So alpha particles, how the alpha particles deflected in this area. Most of the alpha particles are sent in that straight lines, and then one or two alpha particles are deflected in this way. Very few are come back. That is that bounce back of this area. So this is the model of Rutherford. This is called as atomic model. Rutherford generalized these results of alpha particles are scattering in this experiment. So he suggested this is the model of an atom. Rutherford atomic model. What are the details he told regarding the atom? So Rutherford atomic model. Sorry. So Rutherford atomic model means first one, the atom contains large empty space. So atom contains large empty space. So this is the first point of its atomic structure. So atom contains large space. And then positive charge of the mass center of the atom is known as nucleus. Yes, the center part of atom. This is positive charge because the center part of the atom contains proton and neutron. Protons and neutrons are always in positive charge only. So this is the second point of Rutherford atomic model. So the positive charge mass at the center of the atom is known as nucleus. Center of the atom known as nucleus. This is the second point of his conclusion. Third point, the size of the nucleus is very small compared to the size of an atom. Yes, that is also right, because this is the atom. The center part of the part is called as nucleus. Compared to the nucleus space, the atom space is very large. Okay, so the size of the nucleus is very small. Size of the nucleus is very small compared to the atom size. Compared to the atom size, the nucleus size is very small. First point, atom contains large space, and then center of the atom is known as nucleus. The size of the atom, the size of the nucleus is very small compared to the atom size. And next one, protons and neutrons are in that center part. Okay, so the electrons are revolving around the protons and neutrons. So the fourth point, electrons are revolved. So this is also a conclusion of Rutherford atomic model. Electrons are revolved around the nucleus. This is the fourth point of that Rutherford atomic structure. And next one is atom contains protons, neutrons, and then electrons. Protons and neutrons contain the charges. The electrons have no charges. This is the last point. The Atom is a whole electrically neutral because number of protons and electrons and atoms are equal. Protons and then electrons numbers are equal. So this is the last point of that Rutherford atomic structure. So first one is atom contains large empty space, and then positive charge of the mass center of the atom is known as nucleus, and the size of the nucleus is very small compared to the atom size. The electrons are revolved around the nucleus, and then the atom is electrically neutral because the protons and electrons numbers are equal. So the electrically neutral. Protons contains positive charge, electrons contains negative charges. So it is a neutral stage. Okay. So this is the conclusion of Rutherford atomic model. So Rutherford atomic structure is similar to the solar system. Yes, in solar system, the sun is the center part. So just you imagine sun is a nucleus. Around the sun, the planets are around the sun, revolving the sun. Okay, yeah. So all the planets are revolving around the sun. So Rutherford atomic model is similar to the solar system model. The sun is a nucleus. The planets are electrons. Electrons are revolving around the nucleus in atom model. In solar system, sun is considered as a nucleus. The planets are considered as the electrons. So the planets are around the sun, electrons are around the nucleus. So this Rutherford atomic structure is similar to the solar system. So next one is, what is the limitation of Rutherford's model? So next one is limitations of Rutherford's atomic model. What are the limitations? Limitations means the electromagnetic theory moving electrons should accelerate continuously, lose energy. The electromagnetic theory told moving of electrons should continuously, that electrons will be lose their energy. So here also, around the nucleus, the electrons are revolved. So this is the point we know. The electrons are revolving around the nucleus continuously. So the electrons are continuously revolving around the nucleus. So due to this loss of energy, the path of electron may reduce. Finally, electron should fall into the nucleus. So just we imagine the blue part. In first round, the size of the electron is like this. In first round. And then second round, the size will be decreased. And third round, and then more than that first round, the second size is a little bit small. And then third round, it is very small structure. Due to this action, because of loss of energy, always the electrons are around the nucleus. When they are continuously revolving, means definitely the energy will be losses due to the rotations. Okay. So in this kind, the electrons are lost their energy. So the path of the electron may reduced. So the size of the electrons are reduced. Finally, the electron should fall into the nucleus. The size will be reduced and finally they come back to the nucleus, nearer to the nucleus. But it happens because the atoms are unstable due to this action. If it so this is the not acceptable concept for his theory. So atoms are always stable. Rutherford model failed to explain the stability of an atom. So what is the limitation means? So the stability of an atom is not point. So this is the limitation. What is the limitation? Is nothing but the electrons are around that nucleus. So due to this action, the electron will lose the energy. Due to the loss of energy, path of electron may reduce and finally electron should fall into the nucleus. Happens, the atom becomes unstable things. Okay. So first thing, what we understand, what how to the nucleus, discovery of nucleus, how the alpha particles are deflected with the help of that gold foil. What are the details about Rutherford's atomic model, and then limitations of Rutherford's model. And next one is Bohr model of atom. Okay, before that I'm going to show a simulation for you. Yeah. This is that Rutherford scattering experiment. So, in this simulation, we can understand that concept of Rutherford scattering experiment. So, this is the gold foil. So, sorry, this is the gold foil, the circular fluorescent screen. This is, so alpha particles come to this area. So this box contains lot of alpha particles. This is the movement way. This is the path of alpha particle. So yes, start emission is starting. Look at this simulation. The alpha particles are comes from this area. Look, yes, what is the first point? Most of the alpha particles are go through that straight line. So this is the first one. Okay, first point of this atomic structure. The most of the alpha particles through that foil. Some alpha particles are deflected. Look at here. Some alpha particles are deflected. Some of the alpha particles are bounce back to the same position. So this, from this simulation, we can clearly identify how the alpha particles are moved here. So this is the circular fluorescent screen. So zinc coated. So the alpha particles are come here. This is the alpha particles contained box. This is the right way to that moving of alpha particles. The alpha particles, some of the alpha particles are moving in straight line through the foil. Some of the alpha particles are deflected. Some, very few are come back to that area. Okay. So, did you understand, students? Is that clear? How the Rutherford atomic scattering of experiments. This is the model of Rutherford. How the alpha particles are moved. Deflection of alpha particles. Show here. I'm going to start this. Yes. Look at here. So it is very clear. Some of the alpha particles goes in straight line. Some of the alpha particles are deflected. Some of the alpha particles are come back, bounce back. So is that clear? Yes, this is the nucleus. These are all the alpha particles. Some of the alpha particles are move in straight line. Some particles are slightly deflected. Some particles are bounced back. So this is that conclusion of Rutherford atomic model. That is the alpha particles experiment. Okay. Yeah, show here one more simulation for the same concept. Look at here. This is the nucleus part. So the alpha particles are moving here. So the center part, the yellow dot is the nucleus. This is the electron energy level. Alpha particles are moving here. So this is the alpha particle. Trace this area. The alpha particles are moving. Some alpha particles are in straight line. Look at here. The alpha particles are nearer to that center part of the nucleus. Automatically, it will be deflected from that area. So the alpha particle energy level, see this, traces. It will be very clear how the alpha particles are moved. Yes, some particles are goes in straight line. Some particles are moving slightly deflection. Some particles are come back to that area. So when I want to increase the protons and neutrons are in center part. So when we want to change the level of protons means, look at here how the changes are doing here. Just I want to decrease the neutrons level. Now look at that moving of the alpha particles, how the moving alpha particles are, most of the alpha particles are going in straight line. Some of the alpha particles are reflected, some bounce back, return back. So look at here, alpha particles are returned back. The pink color straight line is come back to that area. Next one, see here, it is very clear. Is it? The center part is that nucleus. These are all the alpha particles. The alpha particles are goes in straight line, and some alpha particles are slightly deflected, and then some are bounce back. I want to increase the energy level. When I want to increase the energy level, yes, most of the alpha particles goes are in straight line. So look at the center part. Yes, that proton color is pink and neutron color is white color. The protons, the pink and white is alpha particles. So I want to increase the neutron level means, look at the ball. Neutron level means white part. So the white particles, neutrons are increased mean, look at this area, how the alpha particles are deflected, and how I want to increase the number of protons. The pink color is increased means how the alpha particle deflections are done in this area. So these are all the differences. So how when we want to increase the level of an atom, that is protons and neutrons, means the alpha particle deflections also changed in this area. What is this? Yes, this is that model of Thomson. In Thomson atomic model was also called a plum pudding. So it looks like a watermelon. Watermelon. The center part is that seeds or an electron. Consider as a electron. The red color, that is orange color part is called as that protons or neutrons. Okay, so the center part, Thomson atomic model called as plum pudding or watermelon model. the embedded electrons are resemble the seed of watermelon, and then red moss representative the positive charges. The electrons are always contain the negative charge, remaining protons and neutrons are in positive charges. So the white part is called as electron, and that orange is a proton, and white color, this is neutron. Alpha particles are here. So here also we want to increase the energy level, means look at here, most of the particles, alpha particles are goes in straight way, and then some particles are deflected, some are come back to that area. So this is that model of plum pudding model or a watermelon model. This is the conclusion of Thomson's. Okay. Students, is that clear? So, yes, from the simulation, we learned how the atomic structure, how the model of an atom also. Okay. Students, have you seen this model already? Sriram? Sriram, on clarification, this is the model of an Rutherford's atomic model. In the simulation, we get a lot of details about that, how the alpha particles are moving, that in this place, yes, the center part is the nucleus. This is the electron energy level. Alpha particle raises the, this color of that rays is in pink. Okay. So when we want to increase that energy level of alpha particles, means the deflection, the particles are moving in fast manner. When I want to minimize, that means the energy level is also minimized. When we want to increase the proton or neutron, the center part is the protons or neutrons. We want to increase the level of the neutrons, means the deflection also changes in this area. And then second part, this is that center part, that is called as pink color is denoted as protons and white color is denoted as neutrons. This is the alpha particles. How the deflection is going on here. Here also, we want to minimize the energy level. The alpha particles are moving in slow manner. Some particles are come back, some particles are deflected, very few are in straight line because the energy level is very low. Look at here, most of the lines are goes in straight line. Okay. And then this is the model. And then the second part is plum pudding model. This is the model of Thomson atomic model. Here that white part is called as the watermelon seeds, and this part is watermelons. So the white part, the seed is called as electrons. Remaining part is called as the positive charges, though alpha particles are moving here also. Most of the alpha particles are goes in straight way. Some has come back, some alpha particles are deflected. Okay. So we can get clear idea about that Rutherford's alpha particle scattering experiments. Is there any doubt in this details, ma? Is there any doubt in Rutherford scattering experiments? Next one is Bohr atomics model. Bohr atomic model or atomic structure of the Bohr's model of an atom. Yes, Niels Bohr is the physicist. So he did one experiment. The main postulates of Bohr's atomic model: atoms, the electrons revolve around the nucleus. In an atom, The electrons are revolve around the nucleus. This is the first point of Bohr atomic model. Okay. So, an atom, the nucleus are the electrons are revolve around the nucleus. While the revolving of the nucleus, it is called as an orbit. The electron neither loses nor gains the energy. Rutherford experiment, the electrons are lost their energy, but Bohr postulates are the electrons are neither lost nor gain the energy. Electrons are neither lost nor gains the energy. This is the second point of his postulates. Okay. In Bohr model, the electron, when revolving around that nucleus, and it is called as orbit. That part of that area is called as orbit. So the electron neither loses nor gains the energy. And third point, electrons in a shell can move higher or lower energy, absorbing or releasing, and then fixed amount of energy. So the electrons shell can move around to the higher part or lower energy, the absorbing or releasing amount, some amount of energy. And then name of the shell, the orbits are considered as, this is the important part, the orbits are considered as that letter K, L, M, and then N. K, L, M are the orbits names, and then numbers is 1, 2, 3. A level of the energy. Does K means the number of the level is 1, and then L means it has represented the level of 2, and then M means the number is considered 3, and N is 4. So the energy level is increased. Okay. So these are all the postulates of Bohr atomic model. So Bohr's atomic model means an atom, electrons are revolved around the nucleus. Electrons are neither losses nor gains the energy. Orbits are considered as K, L, M, N. The orbits energy level also considered number 1, 2, and 3, and 4. Okay. How that Bohr's atomic model means the center part is called as nucleus. Okay. How many orbits he told? Yes, there are 4 orbits. So this round is called as orbits. How you can identify that? Yes, the letter K, L, M, and N. Okay, so center part is called as nucleus. Okay, what are the shells? The first round is called as K, and then K shell. Number is N. Okay, it is considered as the energy level is number 1. The second round is called as L shell. The energy level is considered as 2. And this is the third round, that is M shell. The energy level is 3. And this is the fourth one, that is N shell. The energy level is 4. So this is the model of the Bohr's atomic model. So the energy levels around the nucleus in an atom. This is called as Bohr atomic model. How the atoms This is the structure of an atom. Okay. So the orbits are closest to the nucleus, that is called as first shell, K shell. Least amount of energy. So that number is 1 only. The second orbit is called as K shell. The energy level is increased. Third level is called as that M shell, and fourth one is N shell. The fourth orbit as gain more energy level also. Okay. So what is the limitations of the Moore model means? The limitations was applicable only in hydrogen and hydrogen ions. Example, hydrogen, lithium, beryllium, like that. So this Bohr atomic model also not acceptable. Okay, yeah. So what is Bohr atomic model? What are the postulates? The center part is called as an nucleus. The atoms, electrons revolved around the nucleus also. The stationary path is called as orbit. So the round is called as orbit, revolving around the nucleus in an orbit. Electron neither lost nor gain the energy. And electrons, the shell can move to a higher or lower energy when absorbing the energy or releasing fixed amount of energy. So orbits are represented as K, L, M, N shells. Okay, yeah. So yes, we studied the two concepts. One is Rutherford atomic model and then Bohr model also. Okay. Next topic, we are going to learn that isotope, isobar, and isotone. What is isotope? What is isobar? And then what is isotone? First one is isotopes. What is isotopes? Isotope, yes, I think we know about some details about that isotopes. Yes, isotope means number of an atoms, elements have been identified that same atomic number, same atomic number and different mass number. Different mass number. This is the details about that isotope. Yes, atom contains some atoms or some elements of that have been identified, have same atomic number, different mass number is called as isotope. Yes, the examples of isotope is hydrogen. Example is hydrogen. Yes, in hydrogen, first there are some example in hydrogen. Hydrogen means the atomic numbers are same, but that mass number is differ. Protium, deuterium, and then tritium. First one, protium, and then deuterium. And next one is tritium. So these are all the names of hydrogen isotopes. Yes, the center part is nucleus. Nucleus contains protons and neutrons. In protium, contains only one proton in center part. Only one proton and then one electron. So this is hydrogen 1. Superscript and subscript. Okay. Subscript denoted the atomic number. Superscript, denoted the mass number. In protium, only one proton and then one electron. So the atomic number is 1 in protium. Second, in deuterium, The mass number is 2 and then atomic number is 1 only. So, one proton and one neutron. So, one protons and one neutron. Deuterium contains one protons and neutron. How we can calculate the mass number? Addition of protons and neutrons. So, yes, we are calculate that total number of protons and neutron as considered as mass number. So, 1 plus 1 means 2. So, the mass number is 2. That atomic number is 1. So, we can write the subscript in 1 and superscript in 2. So, in deuterium isotope. And next one is tritium. Tritium means 3 in mass number, 1 is atomic number, 1 proton and 2 neutrons. Deuterium contains 1 protons and 2 neutrons. So 2 plus 1. Proton 1, 2 neutrons. So 1 plus 2 means 3. Mass number is 3, but that atomic number is 1 only. So the proton number is considered, denoted the atomic number. So in these 3 isotopes are the same number of protons. There is no changes in this area. Students understands the proton number only denoted the atomic number. So in these 3 hydrogen isotopes contains only 1 proton, so that atomic numbers are same in these 3. That mass number is differ because the neutron number is changed in these 3 isotopes. So first one, protium contains only 1 neutron. Second, deuterium is in 2 neutron. Third one, tritium contains 3 neutron. That is 1 plus 2. So that energy, that mass number is differ. That is neutrons. So the mass numbers are changed in this 3. Okay. Is that clear? Isotope is nothing but an atom or element identified which have the same atomic number but different mass number. The atomic number of all the 3 isotopes are 1, but that mass number is 1, 2, 3, like that. Okay. Some more examples are carbon and chlorine. C612. 6 is the atom. And then next, one more carbon isotope, that atomic number is 6 and then mass number is 13. So this is the one more example for the isotope carbon atom. And chlorine is 35 and 37. Chlorine means 17 is that atomic number, mass number is 35 and 37. So mass numbers are different, but that atomic numbers are same here. So on the basis of these examples, the isotope are defined. Different atoms of same element having same atomic number and then different in mass numbers. Okay. In these isotopes, one more concept, there are 2 types of isotopes, that is stable and then unstable. The stability is changed. 2 types of isotopes, that is one is stable, another one is unstable isotopes. How can we identify the stability of the isotope? Means the number of neutrons are changed. Extra neutrons are added in the nuclei. That stability will be changed in that area. That type of isotope is called as radioisotopes. In isotopes, center part of nucleus contains protons and neutrons. When we want to increase the number of neutrons, means the stability also changed in that place. In that manner, we can conclude that the stable and then unstable isotopes. Okay. So example of radioisotope means uranium 235. Uranium 235. This is one of the important questions. What is the example of radioisotopes? What is the example of radioisotope means uranium 235. So, and then cobalt 60. These two isotopes are used in radiotherapy treatment of radioisotopes. Uranium 235 and then cobalt 60. These two radioisotopes are used in radiotherapy treatment. Okay. Next one is isobar. Isobar is just opposite of isotope. The element contains the same mass number and then different atomic number. Same mass number and then different atomic number. This kind of that element is called as isobar. Okay, so the example of that isobar is argon and calcium. Argon and calcium. Symbol of argon is Ar. Symbol of calcium is Ca. The atomic number of argon is 18. The atomic number of calcium is 20. The mass number of argon and calciums are same. That is 40. The superscript is 40. This is mass number. Okay. This is atomic number. The atomic numbers are differ. The mass numbers are same. So these are all the examples of isobar. Okay, so how it is possible means, yes, already we studied. The electrons are around that nucleus. In center part contains protons and neutrons, that is called as nucleus. In argon and calcium, first one, argon 18 and then 40. So, in center part, 18 protons and then 22 neutrons. Sum of 18 and 22 is 40. That is mass number. 18 protons are denoted the atomic number. So, here is 18. Total is 40. So, that is mass number. There are 3 orbits here. There are 3 orbits. So, in the first orbit contains only 2 electrons. The general electronic configuration is 2, 8, 8 like that only. So, first orbit, first shell contains 2 electrons. So, second shell contains 8 electrons and third shell contains also 8 electrons. So, 2, 8 is 10, 10, 8 is 18. So, total number of electrons are around us 18. The protons and electrons number is always same. So, proton number is 18, electron level also 18. So, this is the structure of an organ. That is the first example of isobar. And next one is calcium. In calcium, the atomic number is 20 and then mass number is 40. So, center part is 20 protons and then 20 neutrons. 20 protons and then 20 neutrons. So, how many orbits? First, second, third, and then four, because number of electrons are higher. Okay, so first orbit contains 2 electrons, second orbit contains the 8 electrons, so 2 plus 8, 10, and then third orbit 8 electrons, and then fourth, just we want to count it, 2 plus 8 or 10, 10 plus 8s are 18, and then remaining 2 electrons are a last shell. Okay, so total number of atomic number, that is electrons number, is 20. 20 plus 20 is 40. That is the mass number of calcium. So this is an example of isobar. So they are different number of protons and electrons, but that mass numbers are equal in both argon and calcium. So they are called as that isobar. Atoms are different elements and different atomic numbers, but the same number of mass number. The mass numbers are same in argon and calcium. Okay. And next one is isotone. Isotope, isobar, and then isotone. What is isotone? Isotone means, yes, number of electrons, and then for the above one example, boron and then carbon. Boron and carbon is the example of isotone. Yes, these two are contains that protons, 5 protons, 5 protons it contains, and then 6 neutrons. Here also 6 protons and 6 neutrons. So in first shell is, first shell contains 2 electrons, and then second shell contains 3 electrons, 5. So protons and electrons numbers are same. And here first shell contains 6, so 2 electrons, and then second shell contains 4 electrons. So in this pair, the elements number of neutrons in boron, number of neutrons in boron, that is 11. 6 plus 5, 6. So 11. So 11, how we can calculate that number of neutrons? 11 minus 6. So 11 minus, 11 minus 5. 11 minus 5 means 6. And then here number of neutrons in carbon also 12 minus 6. So that is 6. So in this example, the elements, that is boron and carbon, same number of neutrons. Say, what are the elements contain that same number? That kind of nature is called as isotopes. Okay, the isotope means same number of neutrons in that element. Atoms of different elements with different atomic number, different mass number, but same number of neutrons. Same number of neutrons is called as isotone. Okay, yeah. So same number of neutrons. Some elements contain that same number of neutrons. So this is called as isotone. Okay, is that clear, ma? Yes, what are the details we studied in this session? First one is Rutherford atomic model, and then Bohr atomic model. What are the postulates and what are the limitations of that? And next one is isotope, isobar, and then isotone. Is there any doubts? Is there any clarification? You please ask me. Is there any doubt, ma? So Now I'm going to explain one small simulation regarding this isotope. Yes, from this simulation, we are going to learn about how the isotopes are. Yeah, this is the periodic table. You know very well about that. Yes, hydrogen, helium, and then lithium, beryllium, like that. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So these are all that examples of that. Yes, what is the symbol is here? Neon. Yes, the mass number is 22. And then atomic number is 10. Yes, we can study one concept, that is the stability of that. Okay. From the beginning, yes, this is hydrogen. Hydrogen is only one atomic number. So the mass number and then atomic AAMU is the atomic mass is 1.00783. So this bowl contains the electrons. Here is proton number is 1. Proton is 1 and then electron is 1. There is no neutron in that hydrogen. Now I'm going to choosing lithium. So lithium means, yes, lithium means the mass number as well as the atomic number. What is the symbol of lithium is Li. The abundant nature of lithium. Yes, the nature of the abundant is 92.41%. Lithium isotopes are abundance. Okay. When I'm going to, now I'm going to adding some neutrons in this area. Yes, this is that instability. Unstable means it is moving in this position. Here also note that unstables. Yes, abundant nature is 0 in lithium 8. The number of mass number is increased because I am adding one neutron here. This is the unstable isotope examples. Okay. Here also unstable. Okay. And next one, I'm choosing boron. Yes, boron level is one of the example of that isotope. Yes, proton numbers are 5. That is that atomic number. And neutrons are 6. And here the symbol of boron is B. Mass number is 11. Atomic number is 5. Abundance nature of that boron 11 isotope is 80%. Sorry, 80.1%. Okay. So here also I want to add one electron. Yes, boron 12 is the unstable isotopes. Abundant nature is 0. Neutrons level is increased. I am choosing carbon. Yes, carbon 12. Yes, we study different number of carbon 12 and then carbon 13 are the examples of the isotope. Yes, this is carbon 12 isotope. Mass number is 12. And then atomic number is 6. Abundance nature of carbon 12 isotope is 98.93%. Okay. And then adding one neutron, that is carbon 13, because it is also one of the second carbon isotope, carbon. So this is the example of that isotope. Here also I want to add one neutron, means so this is the instability. Unstable carbon 14 isotope. Okay, yeah. So from the simulation, how we can, the isotopes are unstable and then unstable positions are attained here. Okay. And next one is oxygen. Oxygen 16. Isotopes are in stable position. And then fluorine, atomic number is 19. This is also unstable. And neon 20 is the isotope. That is mass number is 20 and then atomic number is 10 for that. Neon 20 isotope. Abundance nature is 90.48%. Okay. So I think the isotope and then unstable positions are cleared with the help of the simulation. Okay. So students, please go through the topics. Is there any clarification? We will discuss in next class. Okay. Thank you, students. Jai Vidya Shakti. Jai Bharat. Jai Hind.